Hello all. In the last sessions, we have started with Unit 4, where we have discussed about what is attention and then how do we implement this attention in your transformer sequence to sequence models, right? So, today in this session, I would like to discuss about a simple mechanism called as self-attention and how do we design transformers using self-attention. Okay, so in the last sessions we have discussed about attention mechanism, which is basically used for creating the summary of the input and a specific context. We have seen how attention mechanism works by generating the input tokens into key value pairs, and then we have seen how these key value pairs are compared with an attention function with respect to a query and generate attention weights, which are then converted to weighted sums from which context dependent summary is generated as illustrated in the figure here, right? So we've also seen the transformer model, how the transformer model basically, today in the session we will see how the transformer model basically works for high quality translation. Okay, we have already seen attention mechanism, right? So today in this session I would like to discuss about new mechanism which is called as self attention. Okay, so the basic difference between attention and self attention is the attention mechanism generates the embeddings, the context dependent summary for the entire input. But when I talk about self attention, this creates summary of the entire input, but not one summary for the entire input, but summary for each token. That is, each word will have its own summary generated. Instead of one sentence summary being generated in attention mechanism, self attention will generate summary for each token. As you can see, the attention mechanism will generate context dependent summary, right? That is, for the entire input sentence we get only one summary, right? But the core idea of the transformers or the self attention mechanism is it creates summary for each token of the input. Hence the summary that we create is the input itself. Okay, so as you can see here in the figure below, I have taken three tokens: Maria, No, Daba. So for each word token I am generating summary. So hence I say the summary that I am creating here is the input itself. Okay, now why is this a good thing? Why does it even work? Why do I have to consider self attention is the question, right? Now when I talk about RNNs, which we have created for processing the input sentence in the sequential order through a hidden string, right? So we have seen how do we use RNNs for generating translation. When combined with attention, we even got more good translations for RNN model. But still, they have one issue. That is, the attention mechanism with RNN sequence to sequence model has one issue. Okay, what is that issue? RNN process the input sequentially, right? So when we process the RNN input sequentially, it will become very difficult when we deal with long range dependence between tokens. For one token to another token, if there is a long range dependence, long range gap, when the sentences get longer, so attention mechanism will deliberately fail. Hence, to overcome this disadvantage, we go for self-attention mechanism. Okay. For example, let us consider the sequence. The law will never be perfect, but its application should be just. When I look into this sentence, the word "it's" here refers to law. As humans, we know that the first part of the sentence here is the law will never be perfect. In the second part, when I talk about the pronoun it's is referring to law, right? So whenever I process the same sentence using RNN, when I use RNN to encode the sequence, okay, so RNN needs to learn to remember that the noun law is related to the word it's, which is coming later. But as there is a long gap between the words law and it's, it is very difficult for the neural network to learn about the relation between law and it's. Okay, so let's assume translating Spanish to English language. Okay, and I would like to decode two sentences: Maria no daba. Okay, let's focus on one particular token, which is no. And how do we process this? I give Maria no daba, and then I'll generate embeddings which are represented by WK, and I calculate my key value pairs with respect to query W. With respect to this query, I'll compare my WK to the query with respect to attention function and generate the embeddings which are WQ. Right? So the target here is no word, which is the target word. Okay. Now what do we do? In the first step, we compare the target token against all the tokens in the input. Right? Now, how does self-attention work? Self-attention does this by converting the target into a query by using the projection WQ. Okay, so when it is converting all the tokens into key using projection WK and computing attention weights using function F. Now these attention weights computed by F are normalized and converted to probability distribution by a softmax function. Right. So when I talk about the word it's and law, okay, so the figure below, or the figure as you can see here, illustrates different steps where the attention weights are computed. For words like it's, when it comes to the previous sentence, that will have more weight, higher weights as expected to the words law. Okay, now what do we do in the next step? In the next step, the vector corresponding to each token is converted into a value projected by WV. So as you can see here, in the previous figure, I got only one value, right? As you can see here, we get only one value for self-attention, one value for the normal attention mechanism. But when you talk about self-attention, for each word embeddings, we generate keys. With respect to queries, we compare and generate embeddings for each token, not the single token for the entire input as in this case, but we try to generate multiple tokens for each input in case of self-attention mechanism. That is, each summary produced by self-attention takes all the tokens in the input sequence into consideration but with different weights. So it is therefore very straightforward for words like it's and law to incorporate some part of information in the relation between the two words. So hence self-attention produces summaries through random access over the input, which is contrast to RNN with normal attention mechanism. So by applying this self-attention mechanism to these transformers will become the powerful models for encoding and decoding natural language text. Okay. So the final conclusion here is the self-attention mechanism. Using the self-attention mechanism, we can use only one aspect of the input sequence to generate summaries. Okay. Now, there is another problem with this. If you want self-attention to learn which word each pronoun refers to, it can also do that. How can it do that? By this concept of mixing information from other words based on some other linguistic aspects. How do my self-attention solve this? So this is solved by this mechanism, which is called as multi-head self-attention. As you can see here in the figure below, for each tokens, I am generating multiple keys. Using multiple keys and multiple queries, I calculate my different word embeddings based on attention function. For different word embeddings, I generate different values, different weighted values, and I try to generate different new embeddings from individual words. So this final embeddings that we get are a combination of summaries generated using this mechanism, which is called as multi-head self-attention. Not just single, but multi-head self-attention. Okay. Now, how do I develop transformers? Transformers are developed using this concept of self-attention. Firstly, we have in the first and second session we have seen how do we overcome disadvantages of sequence-to-sequence model with normal attention, and today we have seen what are the drawbacks of attention and how do we overcome that by using self-attention. And now we will discuss about what are transformers and how do we design transformers using this concept of self-attention. Okay, so firstly, to start with, transformers are not designed with one layer of self-attention. Okay, but to encode and decode natural language text with good accuracy, we apply self-attention repeatedly to the inputs to gradually transform them. Okay, as with multi-layer RNNs, The transformer here also groups a series of transformation operations into layers and applies it repeatedly. As you can see, the figure here represents the transformer encoder. I am not just using one layer, I am using two residual connections. I am using multi-head. To the inputs, first I apply multi-head self-attention and I use multiple layers of self-attention mechanism using feed-forward neural networks and try to normalize the input and generate new embeddings. Okay, so the self-attention operation is completely independent of positions. There is another problem here. There is no particular fixed value for each position. That is, even if you flip the words Maria and Daba, because the operation looks only at the word itself, and the aggregated embeddings from other words regardless of where they are, this is obviously limiting. So in order to overcome this disadvantage of position not being placed properly, because when a natural language sentence is processed, it means it depends a lot on how the words are ordered, because there will be no meaning if the words are jumbled, right? Hence, what do we do for this transformer to encode the words in the order? To solve this problem, we generate some artificial embeddings that differ from position to position and add them to the word embeddings before they are actually fed to the layers. And these embeddings that we add are called as positional embeddings, as you can see here in the figure. So before I actually apply my input tokens to the self-attention model, as you can see here in the figure, first I try to generate the words, that is Mariano Daba, and before I apply it to the self-attention, we go for positional encoding. After I give it to the positional encoding, I'll apply it to multi-head attention. I'll take 2 or 3 layers. I'll go for feed forward and then I go for normalization to generate the new embeddings. So just understand that we apply self-attention to transformers. Even you apply self-attention, there is a problem of position of the words. Hence, before we apply self-attention to the input tokens that we generate, we add positional embeddings to the word tokens. Okay. Now, as you can see here in the figure, this is the entire architecture. Okay. Now here, this shows the transformer decoder. This is basically the decoder. As you can see, all the lot is going on. Let's make sure of 2 important things. First, you understand this mechanism called as cross attention. As you can see, this cross attention is between the self attention and feed forward. First, you'll notice one extra mechanism called as cross attention inserted between self attention and feed forward. This cross attention mechanism will actually work like encoder decoder attention mechanism for summarizing the entire input which is extracted from the encoder. So this is the multi-layer encoder block. This is the multi-layer decoder block. So Maria no daba is converted to Mary did not. Okay. So from the encoder we apply cross attention and give it to multi-layer decoder blocks and generate the corresponding output tokens. Okay. So finally here the conclusion is the transformer model generates the target sequence in exactly the same way as RNN sequence-to-sequence model does. Okay. So the decoder here is initialized by a special token and will produce a probability distribution over possible next tokens. That is Mary did not. Okay. So from here we can proceed by choosing the tokens with maximum possibility or keeping the few tokens with highest probability by searching for the entire sentence. Okay. So when you look at the transformer decoder as a black box, it simply produces target sequence exactly the same way RNN does, except that we had changed the concept of adding cross attention in between self attention and feed forward. Okay. So this is how your transformer works with self attention. So understand sequence to sequence models. To overcome the disadvantages, we've gone for attention. Attention will give only one new embedding for the entire tokens. Hence, to overcome this disadvantage, we have gone for self attention, where for each new embedding we generate new different tokens. And using this concept of self attention mechanism, we have designed transformers, which are the most powerful NLP models till date. Okay, so this is all about attention, self attention, and transformers. Thank you.